Okay, lesson 2 of Module 7. This lesson is called Square Roots, and it's part of this larger module about irrational numbers. And so in this lesson, we're going to place square roots of numbers that aren't perfect squares on the number line and hopefully gain some more understanding, and also be introduced to some different symbols that some of you may not have seen, others of you may have already seen. Okay, so square roots is what we're going to be talking about, but we're going to start with a unit square. And so this square here has side length of 1, and it has a diagonal that we're labeling S. Okay, so this diagonal is S, and the square's side length is 1. So since it's a square, we have a right triangle here. S would be the hypotenuse of that right triangle. So one thing I know here is that 1 squared plus 1 squared, both of the legs have a length of 1, is equal to S squared. So 1 squared is just 1. And so we know that for this unit square, the diagonal S squared is equal to 2. S squared is equal to 2. Okay, and so we're thinking of a number, S, that I can multiply by itself to get 2. Okay, so we don't know exactly how big that number is because we know there's not a whole number that I can multiply together to get 2, but we know from our last lesson that if S squared was equal to 4, then S would be 2. And if S squared was equal to 1, then S would equal 1, right? So it's got to be somewhere between S equals 1 and S equals 2. It's somewhere in there. Okay, so this next diagram is going to help us a little bit more with that. So consider, here's our length S on the diagonal. And what I've done here is, well, I haven't, somebody else did, but we've constructed a circle whose radius is this length OA, or S, right? And so we've drawn a circle. So this distance from O out to the radius of the circle is going to have a length of S. So this number S is, sitting here on the number line between 1 and 2. Okay, so this is all pretty much to scale, and so we can see the length of that diagonal right here. Okay, so we know it's greater than 1, but it's less than 2. And in addition to that, we know that it has a precise location. It has a location on the number line, and it's this value right here, right where this point sits on the number line. So it is at a very precise spot. Okay, so I've recreated the number line here on this slide, and so here we have this. Here's our 1, here's our 2, and here's our point for S, which we know is somewhere between 1 and 2. So we can think of other numbers that could go between 1 and 2 here, and I'm just gonna list some of them here, and I'd like you to try to think of some others. So we could say, how about a mixed number like 1.5? Okay, that's a number that could be on the number line between 1 and 2. We could have something like 1.7. We could have 1.25. We could have an improper fraction like well, we could rewrite 1.5 as like 3 halves. And that would be also between 1 and 2 on the number line. Okay, and if we were in class, probably all of you could come up with different numbers that would be between 1 and 2 on the number line. And they would all be either mixed numbers, like 1.5. They would be fractions, like 3/2. Or they would be decimal numbers, like 1.25 or 1 7/10, one of those, which are all rational numbers. Okay, this is what we've talked about as rational numbers. They can be written as a ratio of integers. Okay, so they'd all be rational numbers, all of these that we've listed here. But there's actually more numbers on the number line. There are other numbers between the integers other than these fractions here. So we've seen that some square roots of perfect squares are integers. Like the square root of 4 is 2, because 2 times 2 is 4. But most square roots are going to lie between the integers on the number line. And that's what we're going to look at now. So if we write this symbol, let me just write it with a different color. If we write the square root of b, that means a positive number whose square is b. So I could say the square root of b times the square root of b is equal to b. Okay, so we would say that the square root of 4 is equal to 2. The square root of 9 is equal to 3, because 3 times 3 is 9 and 2 times 2 is 4. So we were trying to find, we had s squared is equal to 2, so we could say that s is equal to the square root of 2. Okay, and this square root symbol, when you see it, it's always going to refer to a positive number. So we could think -3 times -3 is also equal to 9. But when we use the square root symbol for the square root of 9, we're always talking about the positive number that multiplied by itself equals 9. Okay, so let's do a couple exercises, and then we'll come back to our unit square. All right, so you could work on exercises 1 through 4, and then come back and we'll correct them together. So work on those, pause the video, and then we'll quickly go over the answers. Okay, so for number 1, I could say the square root of 81 is equal to 9 because 9 times 9 is equal to 81. Okay, so for the next one, I could say the square root of 225 is equal to 15 because 15 squared is equal to 225. Okay, another way of saying, here I could have said 9 squared is equal to 81. Okay, determine the positive square root of negative 36 if it exists. And I could say it doesn't exist. The number negative 36 does not have a square root. Because you can't have two, there's no number that you could square to get a negative number. Because even if I chose a negative number, negative times negative is going to be positive. Because no number squared is equal to a negative number. It's hard to get this all on the screen. Okay, there we go. So there's nothing that I can multiply by itself to get a negative number. Positive times positive is positive, and negative times negative is positive. So you can't take square roots of negative numbers. All right. Determine the positive square root of 49. Well, the square root of 49 is equal to 7 because 7 squared equals 49. Okay. All right, so we have just been introduced to this symbol, and you may not have seen it. It looks like a division symbol, but it's not. It means the positive square root of whatever number is under the bracket here. Okay, let's go back to our unit square and think about that number that we were talking about, where s squared is equal to 2. And if s squared is equal to 2, then then s is equal to the square root of 2. Because the square root of 2 multiplied by itself is going to equal 2. You can write it like this again. Square root of 2 times the square root of 2 is equal to 2. That's the definition of a square root. It's the number that when I multiply it by itself gives me the other number. Okay? So this is now exact, the square root of 2. We just don't know exactly where it is on the number line. Okay, but we can put it, we can estimate where these square roots would go. Okay? So we're going to look at our number line and we're going to place these numbers. The square root of 1. Let me clear my slide here. Okay, so I'm going to place these 4 numbers, the square root of 1, the square root of 4, the square root of 9, and the square root of 16 on my number line. Okay, so that should be fairly simple, a fairly simple thing to do, right? The square root of 1 is just 1, because 1 times 1 is 1. The square root of 4 is 2. So it goes right down here, square root of 4. Right there. The square root of 9 is 3, because 3 times 3 is 9. And the square root of 4, or square root of 16, sorry, is 4, because 4 times 4 is 16. Okay, so let's get rid of these guys. Okay, now let's place the square root of 2 and the square root of 3 on this number line. Where would you put the square root of 2, the number that you'd multiply by itself to get 2, and the square root of 3 on the number line? So go ahead and pause the video and place it, estimate where you think it would go. Okay, so yeah, maybe you came up with something similar to this. It goes somewhere in here. Thereabouts. So square root of 2, whoops, sorry. Square root of 2 would be less than the square root of 3, which would be less than the square root of 4. So somewhere in there, maybe, you know, this could be square root of 2 could be at about 1 1/3, 1 2/3. Not exactly though, because we could multiply that out and know that it wouldn't multiply exactly to 2, but somewhere in there. Okay. Okay, now we're going to place the square root of 5, square root of 6, square root of 7, and the square root of 8 on that number line. And you do have this in your notes, so I'd encourage you to be writing this in your notes as we go along. Okay, so think about where those numbers would end up on the number line. Okay, so square root of 5 would have to be a number that is bigger than the square root of 4, which is right here, right? Square root of 4 is right here. So square root of 5 would have to be bigger than that. The square root of 6 would have to be bigger than the square root of 5, and then 7 and 8 would have to be in here somewhere. So I'm going to have to write really small right here. So we'd have the square root of 5, and I'm going to write this up here, square root of 6, square root of 7, and square root of 8 would be right here on the number line between the square root of 4 and the square root of 9. Because if you think about it, the two numbers that multiply together, or the number that multiplies by itself to give you 8, must be a little bit smaller than 3, because 3 times 3 is 9. And this is kind of what we did in the first lesson, where we were estimating square roots by finding the nearest perfect square. So if we wanted to know square root of 8, we would say that it was between the square root of 9 and the square root of 4. Okay? The two perfect squares that are nearest. So what's going to go in between these next two divisions? Between 3 and 4, I'm going to have square roots of a lot of other numbers here. So now we're going to place those numbers there. We'd have square root of 10, 11, 12, 13, 14, and 15. Okay, so those are square roots of integers. There's 6 of them, and they're all going to have to go in here. So I'm going to have 1, 2, 4, 5, 6. You can see how this number line is really filling up here. Let me see if I can even write these in. Okay, so I got square root of 10, square root of 11, 12, 13, and I'm just writing them above and below so that I can fit them on my number line on my screen. Okay. Okay, so what we can notice on this number line is that there are some numbers on the number line, integers, as 1. But there are a whole lot more integers like 10, 11, 12, 13 that are not perfect squares, but yet they still have a place on the number line. They have an exact location and an exact value on the number line. But we can't write them as rational numbers like a perfect square, determine which whole number the square root would be closest to, and then use guess and check to move out to greater precision for these. Okay, so work on these independently. You can use a calculator to do the guess and check, but don't just use the square root function on your calculator. Not yet, okay? We want to understand these to maybe a greater depth than using the button on your calculator will allow. Okay, so pause the video and work on exercises 5 through 8, and then we'll correct them together. Okay, so 49 is a perfect square, so I could say that the square root of 49 is equal to 7, because 7 squared is 49. Okay, square root of 62. The closest perfect square to 62 is probably 64, right? So 62 is between 64 as a perfect square, and then the one smaller than that, that's 8 squared, so 49 would be the next closest. 8. We could get it to greater precision than that, though, right? So we know that it's really close. It's pretty far away from 49, which would be the square root of 49 is 7. So we're going to say it's definitely closer to 8. So we could try something like 7.8. So this is the guess and check part of it, right? So 7.8 squared is equal to 60 and 84 hundredths. going to use my calculator for that. I'm not going to take the time to do that multiplication by hand. But so 7.8, I can see, is still too small because this 60.84 is less than 62. Okay, so I'm going to pick a number a little bit bigger. So what if I do 7.9? So 7.9 squared, or 7.9 times 7.9, I'm going to get 62. This is 62 and 41 hundredths. Okay, so that is a little bit too big, 7.9. Now it says give an approximate answer to 1 or 2 decimal places. So this is to 1 decimal place, but I'm going to go one more. I'm going to go a little bit smaller and see how close I can get. 7.8. See, is it closer to 7.8 or closer to 7.9? Closer to 7.9, so I'm going to go 7.87 squared. 7.87 squared. Okay. All right, so this is equal to, now I'm getting really close. It's 61.9369. 9369. So that's going to round to 61.9. So I'm getting really close. 7.87 is a little bit too small. Okay, so I could, so you get the point, right? I can narrow in and get closer and closer by continuing to get closer approximations and checking them. So now what you've probably already done, but what I'm going to do right now, because I haven't done it yet, is to use the square root button on my calculator and double check my work. Square root of 62 is, oh, look at that. It is 7.87400, and it continues. So I've gotten it correct to 2 decimal places pretty quickly just by doing a couple guess and check moves. Okay, so this is the actual answer, and out to the hundredths place I was able to narrow in on it, so that's pretty good. Okay, square root of 122. Okay, so square root of 122, it's got to be pretty close. 121, we remember, is 121 is equal to 11 squared. So the square root of 122 is really close to 11, right? Very close to 11. But is it bigger than 11 or less than 11? Well, it's a little bit bigger, right? So what if I try 11.1? Try 11.1 squared. Okay, so hopefully you've done this process, right? Did you do this on your own? 11.1 times 11.1 is 123. 123.21. So that's too big. 11.1 is too big. So what do I want to try now? Something bigger than 11 but less than 11.1. What number would that be? It's got to have a 0 in the tens place, right? Because that's the only thing less than 1. So it's got to have something in the hundredths place. So what's 11.05 squared? I'm using my calculator here. 11 and 5 hundredths times 11 and 5/100 is equal to 122.1. 0.1025. 1025. So there I have it accurate to 2 decimal places there, 11.05. And if we use our square root button, once again, use the square root button on my calculator, square root of 122 is 11.0453 and more there. So this would round up to 11.05 in the hundredths place. Okay, so I found both of those accurate to the hundredths place just by using guess and check, not by using the square root button on my calculator. Okay, so square root of 400. Do I know what the square root of 400 is? Is it a perfect square? Well, 20 times 20 is 400, so square root of 400 is equal to 20. So that was an easy one. Okay, let's look at question 9. Which of the numbers in exercises 5 through 8 are not perfect squares? Okay, so the numbers in exercises 5 through 8 that aren't perfect squares are 62 and 122, whereas 449 were perfect squares. So 62 and 122 are not perfect squares. And the reason they're not perfect squares is because there's not an integer that I can multiply by itself and get that number, because there is no integer I can square to get these numbers. And of course that's the case with most integers. Most integers are not perfect squares. There are only certain integers that are. Okay, so in our lesson summary, it talks about the fact that we've been introduced to this symbol right here. A positive number whose square is equal to a positive number b is denoted by the symbol square root of b. The symbol square root of b automatically denotes a positive number. For example, square root of 4 is always 2, not negative 2. And the number square root of b is called a positive square root of b. Okay, so remember, negative 2 times negative 2 is also 4. So every positive number has 2 square roots, but when we use the symbol, the square root symbol, we're always talking about the positive square root. And the square root of a perfect square of a whole number is that whole number. In other words, the square root of 25 is 5. However, there are many whole numbers that are not perfect squares. In fact, most whole numbers are not perfect squares. Okay, so good luck with the problem set. This might be review for some of you who had this in a previous pre-algebra class. But it's good reminder. So go ahead and work through the problem set, and I'll see you back here for lesson 3.